So on this slide, I'm going to talk about introduce polar covalent bonds. And as we know from general chemistry, bonds can be either polar or nonpolar. In a nonpolar a covalent bond, the atoms sharing the electrons share them equally. So for example, something like the chlorine molecule Cl2, the atoms are identical, sharing the electrons, so those electrons are shared equally. But when the two atoms sharing the electrons are not the same, like HCl or HF or many other molecules, which we'll see, one of the atoms is likely to attract the electrons more strongly than the other. And the measure of how strongly an atom attracts its electrons is determined by its electronegativity. Okay? Electronegativity is a measure of how strongly an atom attracts shared electrons. Here's a table of electronegativities of some of the atoms in the periodic table. And I'll show you a couple of trends. As you move across a row in a periodic table in the main group of elements, the electronegativity goes up. You know, lithium is 1, carbon is 2.5, oxygen is 3.5, fluorine is 4. And that's the reason for that. As you move across a row, you have an increasing number of protons, positive charges in the nucleus. The size of the atom hardly changes, so that increased positive charge pulls on shared electrons around it much more strongly. You'll also see that the electronegativity goes up as you move up a column, right? The higher up a column you are, the higher the electronegativity. The reason for that is that the electrons, the radius of atoms goes down as you move up a column. And as the radius goes down, the electrons are closer to the nucleus. And so they're attracted more strongly. Okay? You see the most highly electronegative atoms in the periodic table are up in the upper right-hand corner. Right? Okay. So let's look at the consequence of this for bonds. So here are some examples of bonds that range from nonpolar, a CC bond where the sharing of the electrons is the same between the two identical carbons, to a bond like carbon and oxygen where the oxygen is more electronegative than carbon, so it pulls on the electrons more strongly. That shifts the electrons in the bonds closer to the oxygen. And there are two ways to show that. When the electrons move closer to the oxygen and further away from the carbon, the oxygen develops a partial negative charge. And we illustrate that partial negative charge with a delta minus sign. The delta signifies a partial charge. And we indicate the fact that this carbon is now a little electron deficient. The electrons were pulled closer to the oxygen. We indicate that with a partial positive charge. Okay, so we can indicate this charge separation with delta plus and delta minus. And whenever you have charge separation between atoms, we say we have a bond dipole. A bond dipole. That corresponds to a charge separation between bonded atoms that results from a difference in their electronegativities. The other way to show a bond dipole is with a vector, as shown here. The head of the arrow shows the negative end of the bond dipole, the atom with the slightly negative charge. And this end, the tail end, indicates the positive end of the dipole. Okay. In the carbon-lithium bond, it turns out carbon is significantly more electronegative than lithium. Lithium is a metal. Metals have very low electronegativities. So the direction of the bond dipole is towards the carbon, right? So the lithium is positive and the carbon end is slightly negative, right? So the greater the difference in electronegativity between the bonded atoms, the more polar the bond. And so it's actually a spectrum. you start with like CC and CH bonds, which are nonpolar. There's a very small electronegativity difference between C and H, but it effectively behaves, I think it's about 0.4. But CH bonds behave as nonpolar bonds. So you should always remember that a CH bond is effectively, for all extensive purposes, all practical purposes, is a nonpolar bond. And so the NH bond is polar. The CO bond is even more polar. There's a greater difference in electronegativity. And as we go to greater differences in electronegativity between the bonded atoms, the polarity of the bond, the charge separation increases. And at some point, the difference in electronegativity is so large that the electrons are no longer shared. They're transferred to the more electronegative atom. And that's when you get a transfer of electrons, an ionic bond. And so sodium chloride is best to think about that as the electrons being transferred entirely to the chloride, forming chloride ion and sodium cations, okay? As a very rough rule, and this is not a law of science, it's a very rough rule, there are exceptions. When the difference in electronegativity between the atoms is greater than about 1.7, the electrons, you can think of them as being transferred and the resulting formation of a ionic bond. So let's show some bond dipoles in these molecules where they exist. All right, so this is a compound. The CH bonds we said were nonpolar. The CCl electronegativity difference is actually quite small, but the CCl bond behaves very much like a polar bond. Whenever you see a CCl or a CBr or even a C-iodine bond, even though the electronegativity difference might suggest that it's nonpolar, treat it as polar. That's how it behaves. So the chlorine's a little more electronegative. It's a little more electronegative. It's a partial negative, and the carbon partial positive, right? Oxygen's more electronegative than either carbon or hydrogen, so it's negative. Hydrogen and carbon would be positive, right? Oxygen's more electronegative than hydrogen, so you're going to, both these bonds will be polar, right? Cl's a little more electronegative than hydrogen, so that's bond is going to be polar. C double bond O, oxygen's more electronegative than carbon. CH bonds here are going to be nonpolar. We indicated that carbon was more electronegative than lithium. And this is where your periodic table can really come in handy. Now look, check it, look it up. Look it up and verify that these the differences in electronegativity implied by these charge separations are real. Okay? Chlorine is nonpolar. Obviously, two chlorine atoms have to share the electrons equally. And the difference in electronegativity between sodium and bromine is very large. So this really should be thought of as a transfer of electrons and an ionic compound, not a polar covalent bond. Okay. So those are the bond dipoles here. Okay. Okay, so we will stop the recording now.